Any questions from the last class? So we did Cantor's theorem that for any set, and especially for infinite sets, set is much smaller than power set, okay, which means that n is strictly smaller than reals. Natural numbers are far fewer than real numbers, okay, although both of them are infinite. Yes. Good question. It's a question in the assignment. Assignment has only good questions, solve them. Okay. And then we quickly did this notation that we have been using. One is the existential quantification, right, which is basically showing an example in the domain. There exists X. Forgot to do that. And the universal quantifier is the opposite of example. It's basically you have to show that for every element in the domain S or set S, the condition of interest is true, right? So first is kind of an example, and second is about a theorem. And then if you want to show that the theorem is false or the statement is false, then you have to give a counter example, right? So we can formalize that connection. So what is the opposite of there exists X and some property Px? So let me say there exists X in S, property Px. What is the negation of this? Yeah, it means that for every X in the set, property is false. Right, so negation of this example means theorem of the statement opposite to P of X, right? So that's the connection between example and theorem. And same thing if we negated there for all X. Right, this will be, yeah, if the statement for all X is true, then it means that there is a counter example. So there exists X in S such that Qx doesn't hold. Right, so these four statements, four quantified statements are related this way. Right, so look at this connection carefully and don't get confused with what you are trying to prove. Are you trying to prove there exists X, P, Px, or are you trying to prove for all X negation Px, or are you trying to prove for all X P of X, right? So it will be a completely different thing. Any questions about this or the assignment? Okay, so now we will start a different proof paradigm. We have seen contradiction, which is one of the indirect proofs. Now we will see induction. So what is induction? Induction is what you did in programming course, which is recursion, right? Recursion is, yeah, I shouldn't see that maybe. More formally, more directly, it is actually just a for loop, right? The iterative version of recursion is a for loop, but it can also be shown as equivalent to a recursive program. So these three things are kind of mixed up: iterative via for loop, or recursion, or induction. Okay, but in math proofs we always call it induction. The other two things are for programming. And this is a very powerful tool, of course, and you have used it many times. So mathematical induction is like going over natural numbers. Right, so basically you have some statement or some formula that you want to prove as a function of small n. For all small n you want to prove it, so you first prove it for 0, then you prove it for 1, then for 2, and then for 3, and so on. Except that you cannot do this infinitely many times, so you do this more systematically. You first prove it separately for n equal to 0, and then you assume that it is proved up to number n or number I, and assuming that, you prove that it's true for I plus 1. Okay, so if you do prove these two things, I equal to 0 and how to go from I to I plus 1, then what induction principle says is you have shown it for all natural numbers. Right, is that clear? Any doubt? Goes without saying that this thing you can do for integers also, but can you do it for reals? If you want to show something, some statement true for for all real numbers x, how will induction work? How will you say that the real number that comes after x, there also the statement is true? Right, that is more complicated. We will not do that in this course. But that is called transfinite induction. So the uncountable version of this is called transfinite induction. And that also can be formalized, but let's not do that here. So let's just quickly formalize usual induction in one more way, and we'll see some examples. And in all the examples and exercises that you do, you have to follow this strict format. Okay, if you say that your proof is by induction, then you should follow this format which I am defining here. Otherwise, either your proof is incomplete or you are making a mistake. So the format of induction will be written like this. Suppose you want to show that for all x in natural numbers, P of x is a property that you are claiming is true. Okay, this is the whole mathematical statement you want to show. So then you do these two things. Then an inductive proof has two steps. So the first step is usually the trivial case, which is the base case. Okay, so you have to state this clearly. What is the base case that you are claiming. This is very similar to what you do in recursion, right? Recursion also has a base case where the recursion comes and stops and then retraces its path back. So this is, for example, usually it is the case P0. You have to show that P0 is true. Okay, n equal to 0 case. And the other is the usually the harder part, which is induction step. This is really the reason why a theorem is true, where you have to go from n to n plus 1. So we have to show that if Pm is true, then Pm plus 1 is true. Okay, this is the mathematical statement you have to show, the implication. And then you combine these two steps, and invoking the induction principle, you have proven what you started with, which was for all x px. Okay, these two things imply this. That's the principle of induction. That these two imply for all x px. Is that clear? So every time you give an inductive proof, you have to do these two things. So there are many examples. Let's take a very simple one. You want to show that for all n greater than equal to 0, 2 raised to n is at least n plus 1. How do you show this? Right, you can check that for n equal to 0, it is 2 greater than equal to 2, 1 greater than equal to 1. For n equal to 1, it is 2 greater than equal to 2, and then hopefully the same thing for all n, right? So what is the base case? The base case is just checking that 2 raised to 0 is greater than or equal to 0 plus 1. That is fine. And what is the induction step? So assume that 2 raised to I is greater than or equal to I plus 1, or maybe in that notation it's m. 2 raised to m is greater than or equal to m plus 1. And now what do you have to prove with this hypothesis or with this premise? You have to study 2 raised to m plus 1. So 2 raised to m plus 1 is what? Greater than or equal to 2 times 2 raised to m, where you can put m plus 1. Right? And then what? Where do you want to reach? In the end, m plus 2 is where you want to reach, right? So you want to show whether we want to check this, whether this is greater than or equal to m plus 2. So is it? Yeah, this last thing will hold when m is greater than or equal to 0, which we have assumed, right, in the premise again. So this is always true. So which means that we have deduced. So this means that proves that we are done. Is that clear? So that is a pretty simple example. Let's take a more interesting one. A fact that you most probably already know, that any number, natural number, can be written in base 2. Okay, it has a binary representation. So there exists a binary representation which means n equal to B0 plus B1 2, B2 2 square, BR 2 raised to R, such that these BIs, they are 0 1. Okay, and R is some integer, some natural number. Right? So this is about the binary representation or base 2. So do you know a proof of this? Have you seen this statement before? Well, you have done programming, so of course you should know this. In fact, you should know an algorithm to convert n to base 2, right? Is that algorithm a proof? That algorithm is kind of an inductive proof. So here you just have to formalize that as mathematical induction, right? So what do? What is the base case? So let us call this property Pn, right? Let's first identify what we are trying to prove. So we are calling this property P of n, and base case will be P0. So P0 is just the trivial representation, 0 equal to 0, where, I mean, this is the B0 part, right? So, and R is equal to 0. And that's n. So n equal to 0 you can express as just take B0 0 and R is 0. So you only have one digit. So that's the trivial base case. What is the induction step? So assume Pn, that is, you have what the same expression as above, that you have n equal to, or let's use a different, let's not overload variables in proofs. So assume Pm, so you write m to be C0 plus C12 2 to the s, and now what can you say about m plus 1's binary representation? That's the question. What does it mean for m plus 1? Sorry? Yeah, so then it seems to be going in cases, right? So case 1 is C0 equal to 0. So in this case, what will happen? M plus 1 will then be 1 plus and so on. So that is then the binary representation of m plus 1. And what about the other case? So here you are saying C0 is 1. Then what is m plus 1? So is that a good style? So it seems that now when you add 1, C0 plus 1 will become 2, right? And now this will affect C1, which will potentially affect C2 and so on. So, I mean, in the algorithm, the for loop would have just done whatever happens, but here you can't really write down the proof clearly, right? Because it seems that you have to touch all these CIs now. This is not a good proof, so we have to modify it. Do you know how to modify this? No, so you have to do something very different. You don't look at increment of 1, but you look at doubling. So from m prime you go to 2m prime, or you go to 2m prime plus 1. So you look at half of the number, okay? That's more complicated. So let's make those changes. So let's assume that Pm prime we have, and we want to look at two things, 2m prime plus 1 or 2m prime, right? Will this work? If you have the binary representation of m prime, then if once in the induction step you show that you will have binary representations of both twice that and twice m prime plus 1, that again will imply that you have a result for all the n, right? So these will be the two cases. So this, the first one, let's do that. So what is 2m prime plus 1 now? So this is the 1, and you get 2c0 and you get c1 2 square, and what do you get in the end? cs 2 raised to s plus 1. Right, this is valid. So you have basically shifted, and all these CIs were already 0, 1, and the least place you have also 1. What happens with 2m prime? It's even easier, right? This is just 0 plus C02 . So again done. Is this clear? So that is something which you can call a proof, right? The first thing that we were trying, that was more of an algorithm. You can't really write down in a compact, rigid proof style. So you have to come up with a different strategy, and the strategy here is halving. So when you want to show it for n, you should basically look at n by 2, right? And that will depend on whether n is even or odd. So when n is 2m prime, then you have case 2. And when n is 2m prime plus 1, then you have case 1. In each case, you are using property of roughly n by 2 stage. Any questions? So this was slightly non-trivial, right? This is your C program converted into an induction proof. And it's also, I mean, conversely, this induction proof is very constructive. You can implement it as a iterative or a recursive algorithm. Right, the two are kind of, this proof and C program are very similar. Okay, if it's no questions, then let's ask you whether this is unique. Is this representation unique? What do you think? So in this proof, the CIs that you get for n, the BIs which you get for n, is this tuple unique or are there many options? What is the proof for uniqueness? Is this proof a proof of uniqueness? This is not, right, because everything we did here was ad hoc. So this is not really proving uniqueness, it only proves existence. So for uniqueness, you do it as an exercise. It is, so answer is that it is unique. Show that it, give the reason. Okay. Other thing is, induction can also be multidimensional. Okay, that is something which you are doing in, yes. Sorry, say that again. If BR is 1, then what? Yeah, but modulo that cheating. So let's add that here. Let's say that this is the minimal representation. Minimal R. Okay, you can artificially say that R is bigger. I mean, you can just, as he suggested, you can take BR plus 1 to be 0 and BR2, BR plus 2 0 and so on. But then it will be artificially exploding the representation. The minimal representation, minimal R representation, that is unique. And then the only way to duplicate it is by adding zeros. Okay, good point. Yeah, so think about those things and show the uniqueness. Meanwhile, we'll do now multidimensional induction, which means, maybe I should not use n here. N was the parameter, so this is, let's say D. So for D equal to 1, it was, there was a single variable small n that you were changing from base case to infinity. And if D is equal to 2, then you will have two parameters or variables, n1 and 2. Both will change, right? So how will the induction work now? So you have to fix one and increment the other and do this two ways, right? This is again easy to see in programming. If you have a function that is bivariate, then to compute the function you have to reduce to a smaller case in the recursion, right? Same thing now in mathematical induction. So let us do a silly example of this. Consider a function, bivariate function, f m comma n such that f of m plus 1 comma n is m comma n plus 2 m plus n plus 1, and on the other hand m n plus 1 is same thing actually. Okay, so this is a function which is, I mean, is this function well defined? Does it exist, first of all, or is there something missing? Yeah, in the boundary case is missing, right? This, what happens with f 0 comma 0, that you change that and then the function will change. But once we have fixed the boundary or the initial condition values, then after that this recurrence or this recursive algorithm will define f. Will it be a unique definition given the initial condition? It will be unique, right? Because this we are fixing m and then we are incrementing n, or we are fixing n and we are incrementing m. So if you think of these growing rectangles, then f m comma n gets fixed uniquely. There are no two ways of fixing it. So let's give it the initial condition also. So f 0 comma 0 is 0. Okay, now f is uniquely defined, it exists and it's unique. So what is that? Can you guess? Sorry? Yeah, this is turns out to be m plus n square. Then so it means that f is m plus n square. Right, so this is a silly example. I mean, you can see that it will fit. And that is the when you substitute it in these equations and it fits, that essentially is the two-dimensional induction proof. So let us just go through that. So the hypothesis is p m comma n. I mean, basically, or we can just write it here actually. So this is the hypothesis that p, we are calling it p m comma n. We want to show that p m comma n is true. So what we will do here, since our property depends on two variables, so we will first do the base case, which is obviously 0 comma 0. And is p 0 comma 0 true? Because p 0 comma 0 is just saying that f 0 comma 0 should be 0 plus 0 square, which is trivially true, right? That's the definition. It's in the definition. So that's the trivial base case. That showing this, you just have to observe that f 0 comma 0 is equal to 0 plus 0 square. Right side is 0, left side is 0. Right, everything here is equal. So base case is fine, and let's now do the induction step. So induction step is basically move in each direction. Right, so first we move so first you assume that you have to show that Pmn implies say m plus 1 comma n. That is what you want to show here. So what does that mean? So you assume that f m comma n is m plus n square. And then you try to deduce f m plus 1 comma n value. How did you deduce? How will you deduce this? So that is why the first recurrence was given. You plug it in, and you so it's just simply the verification of that. So this is given to be f m comma n. I mean, this is the definition. By definition, it is this. Plus 2 m plus n plus 1, which is then by assumption m plus n square plus 2, which is m plus n plus 1 square. Okay? Does it prove that m plus 1 comma n is p m plus 1 comma n is true? It does, right? So this means we are half done. And do the symmetric thing now. So now, assuming Pmn, you want to show Mn plus 1. So here you are assuming that Fmn is same assumption. And you now have to focus on Mn plus 1. Which is given to be equal to Mn, same thing, which is m plus n square. But let's just skip this, it's the same expression. So what you get is m plus n plus 1 square, right, as in the orange part. And that means you have shown Mn plus 1 is true. Right, so base case together with induction step, where induction step goes in two directions per one per parameter, keeping the other fixed, tells you that you have the claimed statement. Always true. Okay, so these are the steps that you have to go through. Okay, as the problems become more interesting, this will become more complicated. Sorry? This is the unique solution. Did I ask that? Let me first ask it. Yeah, why is it unique? Oh yeah, actually in the beginning I was claiming that the recurrence gives an f and it's also unique. Maybe you are mentioning that point. Why did we say that it's unique? Because yeah, maybe I should not have said that just by looking at the recurrence it is unique. You actually have to prove this. Just by your induction proof, it's not implied. This again will be an exercise. So, I mean, the question is F unique? Okay, the answer is yes, and then you have to give a proof. Can you think of the proof now? What is the proof of this? The proof is actually, you just observe that suppose it is not unique, so there is some other G different from m plus n square. Then the proof that I just wrote here, this will get contradicted. And since I did not make any mistake, there cannot be a different G. Do you see that? That is the proof. So, if G not equal to F exists, then the proof just given turns out to be false, right? Which implies a contradiction. So this contradiction means that F is unique. So it is essentially a proof by contradiction, or you can directly see it as the fact that in the end we deduced F to be m plus n square. So there is no other option. Oh, you are saying since we in the proof we already assumed m plus n square. Okay, that makes it messy. Yeah, that is a valid point. Why did we start with this m plus n square? Yeah, so it will be then a longer proof. Yeah, so let's not claim that this is a proof. You actually have to do this. You have to redo this. Why is it that we actually defined the property P m of n, P m comma n, as f equal to m plus n square? So maybe here we add the question as well. Why this f? Okay, so the reason is that you have to show that actually f exists and it is unique without knowing anything about m plus n square. And then you have to show that now if I substitute m plus m square, it satisfies. So hence this is my f. Okay, it's you have to add steps. Okay, it turns out to be non-trivial. Okay, good. So you are giving formal proofs now, already in the first week. So let me now just quickly give some logical statements. Although you will do these things in detail when you do the course in logic. But it might be good to know these keywords and the connections between various kinds of implications. So mathematical statements we call propositions. Okay, whenever we say proposition or theorem or lemma or corollary or claim or fact, all these things are just propositions. Instead of saying mathematical statement, we can just say that everything is a proposition. And the simplest kind of propositions you get by using these and or not operators. So you can do and, you can do or, and you can do not. Yeah, I should not say that it's about true false. P is some statement and Q is some statement, and you can make a third statement like P and Q, or you can make a fourth statement like P or Q, or you can make fifth statement like negation P, or sixth statement negation Q. Okay, so you using mathematical statements, or maybe expression will be a better word. Using a mathematical expression, logical expression, you can make new expressions by these three operators. Now, what is an implication? So when you write P implies Q, is this a new statement, or can you express it as and or not? Have you seen this? So what is it? Yeah, this is same as negation P or Q, right? Good. So it seems that this and or not, they are complete. You can make this implication, or I mean, if, comma, only if, comma, if and only if. All these things actually can be derived using and or not. And you can check this by what is called a truth table. So check it by a truth table. So what is a truth table? You have value of P, value of Q, and then value of the expression. So when P and Q both are, this will not be visible. When P and Q both are 0, then what can you say about the expression P implies Q? Is it, so 0 means false, right? So now, is the statement true or false? 0 or 1? Yeah, it's 1. And if P is 0, Q is 1, then? Yeah, then again it's 1. And what about 1, 0? Then it is 0. And 1, 1, obviously 1. Right? So these are all the possibilities, and you can see that it matches negation P or Q. Right? So by the truth table of these two, left statement, right statement, you can see that they are equivalent. So that is a very exhaustive way of thinking about such statements. You can do the same for if and only if. And what are the basic rules of inference? that we keep using in our proofs. So, if P is true, then you can deduce that P or Q is true, right? So, if in a proof at some point you reach a statement P, then in the next step you can add any arbitrary statement Q also, and P or Q will be true. So, these kind of simple steps we use in our complicated proofs. Each transition step is of this type, one of these types. Suppose you have P and you have P implies Q. Right? In one step you deduced P, in the other step you deduce P implies Q, then in the third step you will deduce Q, right? So, this rule of inference is so important, it has a name. Do you know the name? This is called modus ponens. So, this we use the most of the time, that if we have shown an implication and we have shown the premise, then we have shown the conclusion. Yes, so I am writing these things as a formula because once it is written as a formula, then you can check that these things are true. Okay, you can just fix values for PQ 0, 1 and you can see that everything is consistent. Okay, so, it becomes like an algebra. What about if I give you negation Q and I give you P implies Q, what will you deduce then? So, for this you recall the contrapositive style of proof. It will give you what? P implies Q is the same as negation Q implies negation P, and if you know that negation Q holds, then negation P will hold, right? What if you have two implications? What will you deduce if P implies Q? You have shown in one step, in the next step you have shown Q implies R, then what can you show in the third step? That P implies R, right? So, these things are kind of obvious, but good to see them in this algebraic form, so you can formally actually prove the connections. Okay, let's move to quantification. Suppose I have shown that there exists an X such that Px holds. Okay, I have to specify the domain probably. Maybe for all X. Suppose I have shown that for all X in the set S, P of X holds. Then from this, what can I deduce? I can pick any C from S. Let me just call it then small s. I can pick any element from the set big S and deduce that the property is true at that, right? And let's do the opposite of this. What if I have the knowledge that P is true at some point small s? Then what can you deduce in the next step? Yeah, then you can deduce there exists an X in S, P of X, right? So, that is the motivation for this quantification. If you know a theorem, then you can instantiate it. So, the first thing is an instantiation. Or you can call it specialization. and the second is merely a translation. In fact, yeah, this is kind of from the definition. There is no name for this. Okay. And what else? I think that we already did. If you negate, what happens? That we already wrote. If you negate for all x px, then you will get there exists x, negation px. But this implication is a special implication, because the converse is also true, right? So you can make it both ways. You can check that these two things are equivalent. So left implies right, right implies left. Is that clear? Yeah, so this is the basic notation. We don't need any more logic formalities, but as the course progresses, this kind of notation I'll use all the time. Okay, so you have to remember where that is coming from. This attempt to formalize and algebraize all the logical statements in a systematic way. Any questions? Yeah, so next let's do this. So next time we will start counting. So next time we'll do basic counting.